Hello, and welcome to Astronomy 100. In this video, we're going to continue our discussion of stellar evolution. And in the last video, we talked about how intermediate mass stars die. And remember, the key things to understand is that when you reach a particular element at the core, that if that element can't get to the fusion process, then that core stops producing energy. And once the core stops producing energy, then essentially the fate of the star is sealed. And what we saw is that the sun will reach a point where it's going to collapse its core very small, but not quite get hot enough to get the carbon to fuse. And then ultimately the envelope expands into space, becomes a planetary nebula, and the core that remains is called a white dwarf. And we saw some examples. Let me show you just a few more in this new video here. Here are many, many other examples of stars that are intermediate mass stars that have completely finished the evolutionary sequence. And you can see that a planetary nebula is quite beautiful. There are many different shapes, many different colorations, although most of these are false color images. But the shapes are dictated by a couple of factors. It's believed that what happens is when the envelope of the star puffs off or gets pushed out into space, that if there's any sort of an interaction with planets or a binary star system in particular, what will happen is it will shape the cloud into something that's rather unique. There are no two that look the same. They all tend to have quite an interesting look to them as their material gets pushed off into space. Now, what I want to concentrate in this video is on one particular idea that is going to really be a segue into the final stages of the evolutionary sequence of high mass stars, which is what we'll get to in the next video. But let's go back to this idea that we ended with in the last video. Remember, this is the Hertz-Sprung-Russell diagram. And what we talked about in the last video is how all of the stars that are down here that are collectively together as one group, these are white dwarfs, or these are the remnant cores of intermediate mass stars that have pushed off their envelopes. And so if you recall, I was able to show you that they're all the same size, give or take. Notice that this line right here, anything that's on this green line is 1/100th the size of the sun. And the reason why we know that is because every value of L and every value of T along this line gives us back the same number for R. So everything on this green line has a size of 1/100th the radius of the sun. So you can say that each one of these stars, with a little bit of a difference, but every one of these stars are approximately the same size. Now, if you do some critical thinking, there's some ideas that pop from this that, of course, lead to more questions. For instance, notice that even though all of these white dwarfs are the same size, notice they're not the same temperature. So these right here, if we go up, anything that's over towards the left has a high temperature. Anything that's to the right has a low temperature. So if you remember on the HR diagram, when you go from left to right, you are lowering the surface temperature of the object. So hot stars, cool stars, and even cooler stars as we go towards the right. So why is it that some white dwarf stars are hot and others are cool? Well, if you think about it, and you remember from the last video, they have ended their existence. There is no internal energy source, but when they are raised up to these enormously high temperatures, they will cool off as time goes by. So there's nothing to keep the temperature high, but as time goes by, they're going to cool off, getting cooler and cooler as time continues. So what you can assume is the ones that are right here, these are white dwarfs that formed fairly recently. And they're still very hot compared to the others. And as time goes by, they will cool off. And as we go down this group, these are cooler and cooler and cooler. And you can assume that these white dwarfs down here, which are cooler, have become that way because they are older. So these are white dwarfs that have had time to cool off, and these are white dwarfs that are fairly recently formed. So now what I want you to notice is, as time goes by, what you can say then is when we go from here to here, we're actually looking at a time interval. These white dwarfs are more recently formed, and these white dwarfs have formed a long time ago. Now let's put those two things together. They're all the same size, but these are more recently formed, and these have formed a long time ago. So if you put those two together, what it suggests is a white dwarf forms, cools off, but notice it's not getting any smaller in its size as time goes by. If they were getting smaller, they would be moving down like this, because remember, this is getting bigger and this is getting smaller. So they cool off over time, but they don't shrink any smaller. So that really makes the question, what really stops gravity from continually collapsing these white dwarf stars smaller and smaller and smaller? Remember, gravity is what squeezed them down to their current size, but what this seems to suggest is gravity gets stopped. Something stops gravity from continually shrinking them smaller and smaller and smaller. Now, this question was one that the astronomers faced in the early part of the 20th century. What would stop the gravitational collapse of a white dwarf star? Gravity has clearly made it that way, but without any internal energy source that is going to fight gravity, take away that energy source, gravity should make these things smaller and smaller and really have no end to the ability to shrink it smaller and smaller. So there was a group of physicists in the early part of the 20th century that tried to explore the details of this and try to come up with an answer. And one of them in particular, in the early part of the 20th century, in the early 1900s, came up with the answer. Let's take a look. The answer that he came up with is the electrons actually stop gravity. Now let me explain what this means. Let's go to a picture here. If we were to look at the material of a white dwarf, remember the material is carbon nuclei. And in my laziness, just because it becomes very cluttered, instead of putting all the protons and neutrons for a carbon nucleus, I'm just going to make one single thing, put a C on it so you know that it's carbon. So this is a carbon nucleus, this is a carbon nucleus, etc. Now if you recall, the normal atoms that make up a star have electrons that orbit around the nuclei. And in the process of fusion, or at least leading up to the process of fusion, the electrons get normally stripped away. And then fusion actually involves only the nucleus. But remember, even though the electrons get stripped away, they don't disappear, they don't go away, they just get stripped away from the nuclei. And in the fusion process, the electron doesn't play any role in the steps that lead through the fusion process. But now that the core has developed a whole bunch of carbon nuclei, those electrons, of course, are still interspersed between those carbon nuclei. Now what happens is the force of gravity is continually squeezing this material, trying to make it smaller and smaller. If this star was producing energy, the flow of energy would push back against gravity and the material would not collapse, or the white dwarf would not get any smaller. But there is no fusion, so something else has stopped gravity. And what was discovered is that there's this property that electrons have that has to do with what occurs when you try to force them to become closer and closer together. For instance, gravity constantly squeezes this material, and in doing so makes it become very crowded. Notice the before and after. Gravity squeezes it and forces the material to become very, very crowded. But in the world of physics, especially in the world of quantum mechanics, there's this rule that says that the electrons themselves have a limit to how tightly you can pack them together. In other words, if you force the electrons to get closer and closer and closer together, squeezing them tighter and tighter so that their freedom to move around becomes less and less. There's a rule that says when you start to make the electrons become very tightly packed together, then they start to resist the fact that you're trying to make them closer together. The tighter you pack them together, the more they resist your attempt to make them closer together. So the electrons have a limit to how tightly they can be packed together. And in physics, there's a very fancy name for this. This is called electron degeneracy pressure. So what happens ultimately is the more you try to compact the material, the more the electrons resist and make it harder for you to compact the material. So electron degeneracy pressure becomes strong enough and powerful enough that it halts gravity. It basically keeps gravity from shrinking the white dwarf any smaller. Now, this very same physicist who figured this out, and I'll tell you more about him in just a minute, also asked a very important question. He said, well, can gravity be so powerful that it can overcome what the electrons are resisting? In other words, the electrons have the ability to resist the compression due to gravity, but is their strength infinite, or can gravity become powerful enough to overcome what the electrons are trying to resist or avoid? And it turns out the answer is yes. Electron degeneracy pressure has its limits. If gravity is powerful enough, the electrons can actually be overcome and gravity can overwhelm the electrons. But remember, gravity depends on mass. So what he calculated is what is the mass necessary for gravity to become powerful enough to overcome the electrons. And the number he calculates is a mass that is in the neighborhood of 1.4 solar masses. Now let me explain what this means, because it's a little confusing if you don't kind of follow the logic here. What he calculated is if the white dwarf, the mass of the remnant core, is less than 1.4 times the mass of our sun today, so 1.4 solar masses, if it's less, then the electrons have the strength to fight gravity, and the white dwarf will not shrink any smaller, and it'll stay a white dwarf for all of eternity. If the mass of the remnant core is greater than 1.4 solar masses, then gravity will overwhelm the electrons and continue the core shrinking smaller, collapsing and crushing it smaller and smaller and smaller. So what he calculated is that all white dwarf stars in our universe should not be greater than 1.4 solar masses. Otherwise, they won't be white dwarfs. So his prediction was all white dwarfs should have a mass less than 1.4 solar masses. And sure enough, in about 100 years of observing white dwarfs, we have never found one that is greater than 1.4 solar masses. So this seems to predict that gravity can be stopped by the electrons of a white dwarf, assuming that the mass of the white dwarf does not exceed 1.4 solar masses. Now, his name, he was from India, from the country of India, and he was somebody who immigrated from India to Great Britain and then eventually came to the United States. But being of Indian descent, his name was Subramanian Chandrasekhar. Yes, that's a mouthful. And so this number, let's go back to the screen, this number is called the Chandrasekhar limit, named in his honor, and it is kind of a hard word to say, but Chandrasekhar limit is the limit of what a white dwarf's mass could be. In other words, no white dwarf shall have a mass greater than the Chandrasekhar limit. And so this becomes a very critical number in astronomy when it comes to stellar evolution. And what we'll find out is that it becomes a critical number in our next topic. Let me show you his picture. So Subramanian Chandrasekhar, and because of this discovery and because of how critical this idea is, he was eventually awarded the Nobel Prize in physics. So he was a Nobel laureate. He died in the year 1995, lived a very long life. He immigrated to the United States and did most of his career at the University of Chicago. So the Chandrasekhar limit is the limit for the mass of a white dwarf star. Now, in the next video, what we're going to do is talk about what happens when a star is massive enough that after it dies, if its core is greater than that Chandrasekhar limit, What happens when gravity just keeps crushing and collapsing and crushing? What does that star become? It's quite interesting when we get there, but we're running a little short of time, so we'll save that for next time. I hope you'll join me.